It turns out that there are dozens of applications of integrals. I would love to tell you that this is a math geek only topic, but if you are going into any applied field, you will see at some point calculus used there. And in particular, integration shows up in places that aren't necessarily intuitively obvious. I want to talk about a couple of different examples in physics and engineering, in biology, in mathematics and statistics, and we'll get through all of these over the course of the next couple of lectures. But I figured I'd start with this physics and engineering idea. The textbook starts with this work and pressure and hydrostatics, which I think is an interesting topic, but I really have yet to find good examples of that in practicality. Center of mass is something I can do pretty well, and I think is an easier idea. If I want you to balance something, well, that's actually a relatively straightforward question if the object is linear of some type, right? I brought my umbrella because it's raining out. It's open. How would you hold it to balance it on your finger? I want to be able to let it go with my other hand. I'm going to have to be close to this end. Why?
Maybe because it's heavier, this left side, we're trying to make it more even.
There's more mass on this left end. I think it's right about the nut. Oh, it's still a little tight. There we go. But the only way to get that point is to figure out how force is acting on this object. Okay. That requires me to steal a bit from the physics department and say that if I've got a number line and I've got a weight and a fulcrum somewhere, the balance point, then this mass exerts a force due to gravity. Now that causes what to happen? Put a weight on one side, what happens to my balance starts to tip.
It tips the heavy side.
So we're going to go down here. The amount of force is then going to change depending on where I put that weight. I've just said that, and that sentence is not 100% true. The force doesn't change, but the amount of twist it imparts on the fulcrum changes. Depending on the distance from here to here, we get a torque. And torque is the force times the distance. But it's easier to think of in terms of the mass and the distance. So let's, instead of thinking of just the torque, let's think of the moment of the torque, which is mass times distance. So this particular weight would have a moment m1, x1. If I want to balance this, there should be a weight on the other side so that my total moment, the force applied on the left and the force applied on the right, is 0. Yes? Question. What if the mass over here is different? Well, there are lots of options involved here. But one of the questions I could ask, instead of saying, where do I put that mass to balance stuff, is where do I put the fulcrum to balance stuff? So let's suppose instead of moving the masses, I get to move the balance point. All right, I need to change a couple things. Those are going to be positions on the x-axis instead of distances. And I'll have a mass here and a mass here. And what I want to find is where to put the balance point. So we're going to give that variable x bar. Well, then the distances that I've indicated up on the top are now here. Distance 1 and distance 2. And I know that the total of those should balance out. So mass 2 times x bar minus x2, because x bar is to the right, it should be bigger, should be equal to mass 1 times x1 minus x bar, because x1 is to the right, it should be bigger. Do me the algebra necessary to solve for x bar. A little bit of algebra necessary. I can rearrange and I can get x bar alone. And this tells me where I should put the fulcrum, the balance point, to balance these masses out and to be able to hold on one finger exactly this whole mass on each side. So we're going to call this the center of mass. By the way, it works for more than one weight, one pair of weights. It works for as many as you want. In general, I would say that what you need to do is you need to take the sum of all of the products of the mass with their positions and divide by the sum of the masses. Because that's what's on the bottom are the masses, and what's on the top, those are those moments I was talking about. Up here, moment being mass times distance. Questions? Move from one dimension to two dimensions. What if instead of just having weights in a line, I have weights spread out in the XY plane? So here, I have three weights. I have a 3-unit weight over in the second quadrant at the point -1, 1. I have an 8-unit weight out at 3, 2 in the first quadrant, and I have a 4-unit weight at 2, -1 in the fourth quadrant. Where do I put a point so that if I connected all of these weights to that point, it would hang flat? Now you may be asking, why the hell would you want to do this? Who's flown out of Pittsburgh? You go onto the air side, you go up the escalator, what's above your head? You come up the escalators, you're going to your gate to go to your plane. There's this lovely mural on the floor, the tile inlay looks like rivers. It's above your head. Oh, I stumped the room. It's a mobile. And it's not just any mobile. It's a mobile by Alexander Calder. It's a set of vanes there. It's a set of vanes on rods hanging up in the air. But it doesn't wiggle back and forth. It hangs perfectly steady. And as you walk underneath, the breeze of all the people moving back and forth causes it to rotate at different speeds. And different pieces rotate independently. This bottom piece down here has several different branches that all turn independently. But what they don't do is this. They don't wiggle up and down. They only turn side to side. How? Because all of the branches are balanced on their center of mass. So, how do I find this point? Well, what I have to do is I have to do this problem twice. I have to think about the moment on the x-axis, which would measure how much left or right I would get. If I need to know where to balance in the x equals, if I write an equation x equals, what is the graph of x equals? A vertical line. But if I have a vertical line, then I'm measuring rotation around a y-axis, aren't I? I hate this terminology. But when I'm trying to figure out the distribution left and right, we call that the moment in y. And if I want to figure out where up and down to put stuff, I'm going to do a horizontal line, right? That's going to rotate around an x-axis. But here's the best part. If I take these items and I also take the sum of the masses, then I can do exactly this calculation. And I can write x bar is the sum mass times x over sum of the masses. And I can write y bar is the sum of m times y over the sum of the masses. So for these particular weights in this particular configuration, I'd like you to do those two calculations. Give me a balance point. Intuitively, this is heavier than both of these. So I would expect my balance point to be closer to this and further away from these. But let's see what we come up with. Not that long an addition. What do you get? Mass times x for the first one, I'll work left to right. So that's 3 times negative 1. And then 4 times 2. And then 8 times 3. And then down here it's just the weights, 3 and 4 and 8. So the bottom is 15. What's the top? (32 minus 3 is 29, which is just a little bit shy of 2, right? Yes.
How are you getting an 8, 4, 3?
Those are the weights associated to each spot. I had to give them to you in the problem. That's why I set it up that way. What about over here? You got it. But now in those second set of parentheses, instead of x coordinates, I put y coordinates. The 3 is at a height of 1. The 4 is at a height of negative 1. The 8 is at a height of 2. So that's 3 minus 4 plus 16. It's 15 over 15. Yay. Let's physically draw that spot on my coordinates. We said this was just a little bit less than 2. And this is up here at 1. So back over to the left a little bit. If I were to put a set of rods, each of those 3 from that spot, balance the entire thing on the tip of my finger. Even though 8 pounds versus 4 pounds versus 3 pounds, you'd expect it to tip. Nope, I've adjusted and accounted for that. Questions? This is neither a set of disjoint weights nor a set of flat weights. So if I really wanted to be pedantic, I should go from 2 dimensions to 3 dimensions. We'll save that for another time. But this is not separate individual weights. It's a single solid object. How do I move from a set of discrete weights to a continuous item? How do I know to put my finger? Balance this. And what if it's not a rectangle? What if I just picked some weird shape? Here's an absolutely bizarre shape in the XY plane. Now I'm going to make an assumption. The assumption I'm going to make is that whatever you drew this shape on, when you cut the shape out, it's uniformly thick and uniform density. We call such a thing a lamina, a layer, from which we get the phrase laminate, like the surface of the table in front of you is a thin piece of material glued to the surface of the wood. I would like to find the balance point so that I can play the same trick and balance this shape on my fingertip. Page 560, figure 5. Where is that point P in this shape? With the uniform dense idea, I'm going to call this point our center of mass. A centroid. If your object is not of uniform mass, then you would need to take into account density somehow. We'll save that for the moment. For right now, I'm just dealing with a uniformly dense idea, so I'm thinking just really about the shape of the object. Okay. First question, who gives a fuck? Why do I care? You went to state college this weekend. You didn't teleport. You drove. How was the ride? Tell me about your wheels on your car. And that means that you got to adjust your steering to deal with the car trying to move in ways you don't expect it to. When you go get your car aligned, when you get tires, what do they do to your tires? Yes. But what else can they do? A something and alignment. There's another word in there when you go to the car shop. They balance your tires. They're literally adding weights at different spots around your tire so that the centroid of your tire is right in the middle of the axis so it rotates properly. If it doesn't balance, then it wobbles and you drive even worse over those bumpy bridges and crap. Who gives a damn? I drove to work today. I don't want to die. I have a crankshaft in my engine. Same deal. I need the centroid of all of that mass to line up with the physical center of the axle. A crankshaft turns the pistons, as the pistons move up and down, it turns that to be rotation. So that it will turn in the wheels as opposed to just going bang up and down. A crankshaft. Before batteries, people would start a car by cranking it. They were literally rotating the crankshaft to start the pistons compressing the fuel to make it go bang. That's how diesel engines work. They don't have spark plugs. The compression is enough to ignite. Like compressing air in a piston fast causes a spark. I was a science geek before I was a math person. I have a yo-yo. I left the damn thing in my office. The center of mass makes it spin longer if I know where that center is. If it's off center even slightly, it shatters, shakes and wiggles in bad ways. How am I going to find this? Now that I know why I'm looking for it, how am I going to find it? We'll approximate. I'm going to take that shape and I'm going to lay a grid over it. Instead of drawing it on a piece of paper that's regular, I'll draw it on a piece of graph paper. And then in each box, I can say how big is the box, and each box is uniformly dense. So if I know how big it is, I know how much it weighs. So I can take each box and I can say, we're going to put a mass in the center of that box. And we know the x coordinate, y coordinate of that box. And then I'm back to the previous problem, aren't I? And my center of mass can be found with these calculations. But now I've got a whole bunch of masses and a whole bunch of x's and y's, and that's an approximation. How do you make an approximation better?
Making more boxes.
Which means making the size of each box. And if I really wanted to do this like calculus people would, I'd let the size of each box go to 0, wouldn't I?
Gee, this sounds awfully familiar.
Then these sums become Riemann sums, and that makes this an integral problem. And if I do that, then my moment is now the integral of this shape. Well, that's going to be defined by some curve, right? But I need that extra x in there. I need the x coordinate. And that's going to work. And then the mass is just the area. Which means I can find x bar by doing these two integrals. Directly. Like it. That makes sense, I think. Instead of doing a sum, I do an integral. Maddie, what are you trying to see? That because I'm just doing this calculation, right? mx and m. But if I want to do this calculation, I need a y, right? If I wrote this as functions, y is f of x, isn't it? So that means that top is f of x times f of x. That's f of x squared. That's going to be too big. Turns out it's too big by exactly a factor of 2. So I have to have a 1/2 in there. Y times f of x. But y is f of x, so I get f of x squared.
That's second integral to m, that's still a to b, right?
Yes, all these three of these integrals are a to b.
I thought it was a to y.
Oh, no, that's a b. Almost looks like a flat the way I've drawn it. I apologize. Crappy handwriting. Now imagine if I wasn't writing with one of these fountain pens. This is why I don't do my lectures on iPads, because my handwriting on my iPad sucks even worse. All right, wait a second. I get x bar by doing this over the mass. I get y bar by doing this over the mass. Now this is, at the moment, strictly theoretical. So let's actually make this a little more practical. I'll give you a shape. Here's a circle of radius 4. And I'm just looking at the upper half of this circle. So I want to balance this. Okay. Before I do any calculus, I need an x value to balance this. I need a y value to balance this. Where do you think the x value should be to balance this?
I think it is 0.
That makes sense, right? It's the same on the left as it is on the right. So if I'm lucky, x bar should be 0. How about y bar? Do you think it should be high or low? Why? There's width lower, there's less width up top, so I might think that it should be lower rather than higher. So again, if I'm matching my expectation, I think it should be below 2, whatever my number turns out to be. It should be smaller than 2, a little bit lower rather than higher. Let's try. Let's find out. I need 3 integrals. I'm going to start with the one that is the most direct, which is the mass. The mass is the same as the area of this. Integral from -4 to 4, f of x. What's the equation for this damn thing? Leo?
Maybe minus x squared plus 4.
Almost. That would be a parabola, not a circle. They both have to be squared. So it would be x squared plus y squared equals the radius squared. So if I take that and I rewrite it, I get y squared is 16 minus x squared. When I take the square root, it's the square root of the whole thing, Leo, and I cannot simplify the square root down.
60 minus x squared in half.
Right. But for the moment, I'm going to write it just like that. Now, problem number 1. That integral sucks. Because that's a trig substitution, right? But I don't have to do any calculus. Why? Because I'm a cheating mother. Yes, this is a half a circle. What's the formula for the area of a circle?
3 pi r squared.
And I want half of it. I don't have to do the calculus. 1/2 pi r squared. Oh, good. Whew. Okay, now I know the mass. Careful. So now I need to do the moments. I need to do the integral with the x, and I need to do the integral with the y. So let's do the integral with the x. Again, this is our moment left to right, which is why it would balance around a vertical line, which is why they call it ny. I hate this. I just say I'm remembering I'm doing the integral with the x in it. How do I do that?
I was thinking maybe you could do it at u and if u like 16 minus x squared and d 50.
Let's run with that u sub. U equals 16 minus x squared. Du is 2x dx. Wait, it is a minus sign. I don't have a minus 2, so I'll swap. So I get the integral square root of u du with a negative 1/2 in front. I have not written something down yet that we need. The bounds. I did a u sub. Let's switch the limits. Trust me, switch the limits. How do you switch the limits again?
You plug in the lower bound of x and the negative going upper bound before.
Okay, so if x is negative 4, then u is? Zero. And if x is positive 4, u is? I'm doing the integral from 0 to 0. What's the value of this integral?
0.
Which is what we wanted, because that tells me that x bar is 0.
So if you're doing this one exam, we wouldn't even have to sub back in, you could just like sense the integral.
Yep. I could even go a step further. If you think back to this version of the integral, graph that, and you'll see that it's odd, which means that the area on the left is negative and the area on the right is positive, and they're exactly the same size, so that integral is 0. So there are lots of different ways to see that this integral is 0, but that agrees with the intuitive idea that this should balance right in the middle from left to right. I'm happy about this. Now, let's do the other integral, the one with the y in it. All right, it isn't y, it's 1/2 function squared. Mx is the integral from negative 4 to 4, 1/2 square root 16 minus x squared, squared dx. This problem is rigged. Because I'm squaring a square root. Poof. Power rule. 1/2. I plug in 4. 16 times 4 is 64. 4 times 4 times 4. Well, that's 16 times 4. That's also 64. 16 times -4 is -64 minus 1/3 times -64 again. All right, so I'm going to get some arithmetic issues here. 1/2. That's 2/3 of 64. That's 128 over 3. Minus. This negative and negative becomes positive. So that's negative 2/3 of 64. So that's negative 128, but it becomes positive when I subtract here. So that's 1/2 of 256 over 3, which is 128 over 3. That's the moment. That's not y bar. How do I get y bar from the moment? I put it over the mass. 128 over 3 over 8 pi. Which is the same as 128 over 3 times 1 over 8 pi. I can cancel here. 120, 64, 32, 16 over 3 pi. Somebody give me a decimal for that. Leo?
16.755.
I think you forgot a set of parentheses around the bottom. What you gave me was 16 over 3 times pi.
16 divided by 3 pi.
But if you write 16 divided by 3 pi, your calculator does this. You need to write 16 divided by 3 pi.
1.697.
Which jives a little bit more with what we wanted. It's a little bit under 2, isn't it?
Can you explain again how you have to be a little less than 2?
Oh, let's go back and look at the picture. The halfway point of this circle is at a height of 2. So if I think of the part that's above the circle, that halfway point, and the part that's below, which of those is bigger?
So it's just saying if you were to turn it and try to balance it this way.
Right. Remember, I want to put one finger, right? So it not only has to balance left to right, it has to balance top to bottom. So where do I put my finger? It's got to be lower rather than higher. So my center should be down here somewhere. As a matter of fact, I think it's a good practice before you do any calculus to physically look at the region and try and figure out, well, where would I balance this thing? Because this is another piece where I get to say that calculus is physical. I need to be able to hold this in my hand. And in one sense, that's why I save all of these cardboard backer boards from my writing pads. I'll cut shapes out of this sucker to physically try and figure out where stuff should go before I do the problem. Even if you just cut it out of a piece of paper and try and hang it in some fashion, where would you put the pin so it hangs uniformly? Questions? Here's a piece of the plane cut out by a parabola and a line. Well, now I don't have just f of x, I have f of x and g of x. So again, I could ask the same question. Where's the balance point? From left to right, where do you think the balance point should be? Not obvious, is it? From top to bottom, do you think more should be up or more should be down? If it helps, here's the halfway point. Do you think more of this shape is above the horizontal line or more of it is below the horizontal line?
Like more is below it.
So if more is below, I would expect y bar to be less than 1/2. Do you think more of it is to the left of the vertical line or to the right of the vertical line?
Maybe slightly to the right.
So it should be pretty close to 1/2, maybe a little bit bigger. We now have an estimate. It should be somewhere here-ish. Pretty close to 1/2 left to right, but a little less than 1/2 top to bottom. I have to change the integrals because there are two functions now. The mass is now the area between the curves. Chapter 6, section 1, we did that last semester. And that means when I go to do the x integral, I just take the x and put it in there. But when I go to do the y integral, instead of squaring the whole thing, I square each of them separately. So I don't take f minus g and square it. I do f squared minus g squared. Now, I'm not actually going to do this example because it's in the textbook. I believe it's page 568. No. It's page 564. And look, there's the dot. And here's our answer. 1/2 for the x and 0.4 for the y. So it is a little bit down, but it is perfectly balanced left to right. If I have a physical object, I can find its center of mass without any calculus. Take your object and hang it. And from the place where you are hanging it, draw a line straight down. Then pick another point and hang it. And from that point, draw a line straight down. Where the two lines cross, that's the center of mass. And that works no matter what the density is, whether it's uniform or not. On our Canvas page in the web links section is a video from the MIT Science Lab on center of mass experiments, where they throw objects in an arc and they put a little glowing dot on the center of mass. I think they use a tennis racket. And if you throw a tennis racket, it wobbles all over the place. You turn the lights out and just watch the center of mass and moves in a perfectly parabolic arc. If you throw a boomerang, the center of mass of a boomerang is not in the boomerang, it's inside the curve. By the way, it turns out that centers of mass are related to volumes of rotation. There's a result called Pappus's theorem. if you take a region entirely on one side of a line, and rotate it around that line, then the volume is equal to the area of R times the distance traveled by the center of mass. And if you're rotating, the center of mass moves in a circle. All you have to know is how far the point is from the line. Then you can find the volume without doing calculus. This is a result of something called Cavalari's principle, which is about volumes of shapes in general and cross-sectional analysis of those. Cavalari's principle comes into play in a lot of volumetric discussions in chemistry and physics. I'll do biology on Friday, but tomorrow, question and answer. So I'll see you then. A wonderful rest of your day. And I'll bring my toys tomorrow, my boomerang and my yo-yo and all the other stuff I have.